ხილა რო გააკეთოთ და ისე ჩაწეროთ, რომ ხო, აი დრაიზე რომ მე აიტვირთება და რაღაც. მადლობა.
თავიდან დავიწყო, თუ რა მითხარი, არ გესმით
ჩემ. ანუ მოკლე მიმოხილვა რომ იყოს, რაც აქამდე
მაგას არ ყვები ახლა, მოკლე მიმოხილვა წინა ლექციის მიმოხილვა. I again re-explain this previously.
დიდი მადლობა.
About
no, this I mean.
Problem.
Several sentences you said, I mean.
About this reabsorption.
Yes.
Lecture. Reabsorption, which are need 3 pressure. First is blood hydrostatic pressure. Difference between afferent and efferent arterioles diameters, which are makes this blood hydrostatic pressure or plasma hydrostatic pressure, which are 60 millimeters of mercury, and 2 opposite pressure. One, ultrafiltrate hydrostatic pressure, 15 millimeters, and second is blood plasma oncotic pressure. Net filtration pressure is 60 minus sum of 2 opposite pressure, 15 plus 28. Sometimes is a net filtration pressure is 17 millimeters of mercury. Increase this net filtration pressure, increase this glomerular filtrations rate. And decrease also opposite, decrease glomerular filtration rate, which has auto-regulation mechanism. Also it regulate, which has this myogenic mechanism, sympathetic nerves regulate, which are from regulate this diameter of afferent arteriole, and this glomerular filtration rate also are sometimes vasoconstriction afferent arteriole, sometimes are vasodilation, which are also help from auto-regulation, this renin, which are produced from juxtaglomerular apparatus. All lecture I repeat, but it's more important. Juxtaglomerular apparatus, which has this afferent arteriole, efferent arteriole, and macula densa cells, and juxtaglomerular GJ cells are producing renin, and this always, then all steps, renin, which are first time travel in plasma, are converted angiotensinogen from angiotensin 1. Then angiotensin 1 binds this ACE receptors in the blood vessels, example in the lungs, convert with angiotensin 2 and angiotensin 2, which are vasoconstriction of the arterioles diameters, and also help release this aldosterone from this adrenal glands. Now, these are regulation of GFR or glomerular filtration rate. These are previous lectures material about this filtration, and the next after filtration, which are filtrate how much? 180 liters. This 99% of the filtrate are return to the vascular systems. Which vascular systems you know? Around this proximal convoluted tube and distal convoluted tube has this peritubular capillaries, which are continuous or after efferent arteriole. Yes, it's peritubular capillaries around this proximal convoluted tube and distal, and in vasa recta around this and around this loop of Henle is a vasa recta. 2 types of blood vessels which are made from efferent arterioles. And this some substances are reabsorption in proximal convoluted tube, and you know in proximal convoluted tube and in distal and the loop of Henle of descending and ascending part has different types of epithelial cells. In proximal convoluted tube are simple cuboidal epithelial with many brush borders. When reabsorption these substances, no example, glucose, amino acids, many ions, water also, are this way, which is way? First, it go from this lumen of this tubula, first time luminar membrane, next inside this epithelial cells, the simple squamous cells, which are has this two membrane. First, luminal membrane, and this end of these cells are basolateral membrane. After basolateral membrane, it go in the interstitial fluid between these blood vessels and these cells of the tubular cells. And then enter in example in these peritubular capillaries endothelial cells by simple diffusion or different types of transport. Transport are many types. One, these names is active transport, and second is a passive. Primary, secondary active transport, facilitated diffusion, I explained late. Volume, it's 1% of only is excreted in the urine. No, 1% of 180 liter is 1.8 liter is a 1% which are excreted in the urine. Another all are reabsorption in this the different part of this nephron. A volume of 400 milliliter of urine per day is a minimum needed to excrete the metabolic waste produced by the body. This is called the obligatory water loss. No return of filtrated molecules from the tubules to the blood is called reabsorption. No, I tell about reabsorption. 85% of the 180 liter of glomerular filtrate formed per day is reabsorbed in a constant, unregulated fashion by the proximal tubules and descending limb of nephron loops. But descending limb of nephron loops is different types of epithelial cells. Yes, it's a which type? Simple squamous epithelial cells. After the simple cuboidal cells, which are present in this proximal convoluted tube, then change with this simple squamous epithelial cells. Now, the functions is also easy with descending loop. It's permeable to water. And this ascending limb of loop of Henle and also distal convoluted tube has this same proximal convoluted tube, simple cuboidal epithelium. But small difference are also has with the two type of simple cuboidal epithelial cells. This reabsorption as well in the regulated reabsorption of the remaining volume of filtrate occurs by osmosis. You see this glomerulus with your afferent arteriole, efferent arteriole, this capillary tuft, and these are proximal convoluted tube. No filtrate about filtrated membrane, you know, filtration membrane, which has this three parts. These are inside first fenestration capillaries, then acellular basement membrane, and inside this filtration slits is a space between pedicels, which are covered with this diaphragm. And these are space we are locations is ultrafiltrate. Ultrafiltrate is a provisional urine. Provisional urine is a blood plasma only without large proteins, but large molecules of protein. You know, this barrier with this filtration membrane are barrier, but not has this charge barrier. It also has this diameters. If large molecules of proteins did not filtrate in this filtration space between this visceral and parietal layer of Bowman's capsule. Next, these are proximal which continue in proximal convoluted tube when are reabsorption function. Filtration and reabsorption, plasma, water and is dissolved solutes except proteins, enter the glomerular ultrafiltrate by filtration. But most of these filtered molecules are reabsorbed. The term reabsorption refers to transport of molecules out to the tubular filtrate back into the blood, and which is substance which are no, because all plasma solutes, with the exception of proteins, are able to enter the glomerular ultrafiltrate freely. This total solute concentration or osmolarity of the filtrate is essentially the same of the plasma, 300 milliosmol per milliosmol, milliosmol, 300. I remember it's a plasma osmolarity, 300. Same this ultrafiltrate, but ultrafiltrate is a plasma. And osmolarity is one of this factor is a salt, and salt and concentration in this ultrafiltrate are same with the plasma, but also are same osmolarity. And this filtrate is said to be isosmotic with the plasma. Iso means same with this plasma osmotic pressure. Reabsorption by osmosis cannot occur unless the solute concentration of plasma in the peritubular capillaries and the filtrate are altered by active transport processes. This is by the active transport of sodium from the filtrate to the peritubular blood. First, which is type of ways. I tell about the way which are go the substance or water. Reabsorption across the tubular epithelium into the interstitial fluid includes active and passive transport. Now, which is first transport across the tubular epithelial membranes, tubular epithelial membranes, into the renal interstitial fluid, and then through the peritubular capillaries membrane back into the blood. I open how many types transport are. I open and you see how many type transport from this some of these molecules and water.
Once the filtrate is formed, the early tubular segments of the nephron reabsorb solutes and water back into the blood to restore its volume and composition. They also remove some solutes from the blood and secrete them.
A reabsorption pathway are two types. Transport
to be reabsorbed into the blood, substances in the filtrate must cross the barrier formed by the tubular cells.
By tubular cells. 1 minute, if you open, these are transcellular pathway through the luminal and basolateral membrane, and paracellular pathway through the tight junctions. Like this, what is it? These are lumen of this proximal convoluted tube. These are simple cuboidal epithelial cells with your brush border. These are named basolateral membrane, and these are named luminal membrane, which are in this lumen, yes, basolateral membrane, tight junction between cells of simple cuboidal epithelial, then interstitial fluid, and these are blood vessels with your also endothelial cells, which are one layer of simple squamous epithelial cells, as this way. If you go through the luminal one membrane and then enter in the cytoplasm, then second membrane through the luminal membrane and basolateral membrane, it's named transcellular pathway. Between the cells has these tight junctions. If paracellular pathway through the tight junctions, as this type transport are named paracellular pathway, transcellular or pathway. Okay, 1 minute, I enter again.
The relationship of glomerular filtration
No, these
and
are
tubular
reabsorption, tubular reabsorption.
To be reabsorbed into the blood, substances in the filtrate must cross the barrier formed by the tubular cells. There are two reabsorption pathways, the transcellular and the paracellular. Most solutes that are reabsorbed use the transcellular pathway. They diffuse or are actively transported through the luminal and basolateral membranes of the tubular cells into the interstitial space and then into the paratubular capillaries. Click the arrow to see an animation of the transcellular pathway.
First transcellular pathway.
The second pathway is the paracellular one through the tight junctions into the lateral intercellular space. Certain tight junctions are not as tight as the name implies and will allow this pathway while others will not. Click the arrow and follow it through the paracellular pathway.
And paracellular pathway, no, between tight junctions. Okay, I repeat these two types of pathway. First, transcellular, and you see luminal space. These are proximal convoluted tubules inside. These are around these simple cuboidal cells, which has this luminal membrane and basolateral membrane. Between this proximal convoluted tube, and these are peritubular capillaries, yes? Peritubular capillaries, which has this one layer of endothelial cells. This way has this transcellular through the luminal membrane and basolateral membrane, then interstitial fluid, and after enter in the blood vessels. And second, paracellular pathway through the tight junctions, which are between these cells. No, two types of cells. No reabsorption overview, this diffusion. For diffusion,
the previous topic, glomerular filtration, demonstrated that the force driving the formation of the filtrate is blood pressure within the glomerulus. We now turn to the question of what drives reabsorption, which reclaims the valued substances. Let's begin with the reabsorption of water by diffusion. For each of the following questions, select the correct answer by clicking the appropriate box. How can we cause water to diffuse from the lumen through the tight junctions of these generic tubular cells into the interstitial space?
Two questions. Decrease the osmolarity of the interstitium or increase the osmolarity of the interstitium?
Decrease the osmolarity.
No, increase.
Increase.
1 minute. Osmolarity.
Decrease.
Yes, okay, 1 minute. Explain. But osmolarity increase when in interstitial fluid enter salts. Yes, sodium ions example, and doesn't. And if enter water, then interstitial fluids are...
No, this will cause water to enter the tubule from the interstitium, causing further dehydration.
Further dehydration. Increase the osmolarity.
Yes, water will move from its higher concentration in the tubule through the tight junctions to its lower concentration in the interstitium. Water will also move through the plasma membranes of the cells that are permeable to water.
Permeable to water. And how are you, what is this questions? Diffuse from the lumen through the tight junctions of this general tubular cells into the interstitial space. Tell about this lumen. Yes, in interstitial space, when enters this, increase the osmolarity of the interstitium. Okay, next is this osmolarity, reabsorption, and you see about reabsorption in osmolarity.
The next question then is, how can we increase the osmolarity of the interstitium?
How can we increase the osmolarity of the interstitium? My two types of answers. Why you answered is incorrect.
Transfer water from the cell into the interstitium.
First, transport water from the cell into interstitium.
Yeah.
No, it's the first option.
Okay, I think it's the answer. Why sodium ions? Transport sodium ions from the cell into the interstitium. Sodium ions. So transport sodium, I explained small after this slide. Yes, water, if permeability only water, it's decrease osmolarity in the interstitial fluid if we go more water. But instead of water, are which is click? Tell me, answered which first time, which click, first or second?
First.
First. Yes, I transport sodium ions into the interstitial will rise the osmolarity, not only water. Water permeability is not increase the osmolarity, but sodium ions into the interstitium will rise the osmolarity. Water will then diffuse from the tubule through the tight junctions and the permeable plasma membranes into the interstitium, equilibrating the two osmolarities. What helps this equilibrium, osmolarity in the interstitial fluid and plasma? And the sodium ions, which are transport into the lumen to this. But these are different types of transport. Yes, sodium ions from the cell into the interstitium are increased osmolarity. Next, reabsorption of membrane of active transport.
Is, how will the reduction in the intracellular sodium ion concentration resulting from the basolateral transport affect the activity at the luminal membrane?
Two options. Additional sodium ions will also leave the cell by moving into the filtrate through the luminal membrane, or sodium ions will move from a higher concentration into the filtrate into the lower extracellular concentration. Which options you think is correct? First or second? Did not have answer.
I think sodium will move from the higher concentration in the filtrate into the water.
These are
the transport
correct.
of sodium ions through the basolateral membrane will cause more ions to be reabsorbed through the luminal membrane.
More are reabsorbed from the luminal membrane. And next you see this reabsorption of sodium ions in this luminal membrane.
To summarize, the transport of sodium ions has two important direct results. One, the interstitial osmolarity increases, causing water to diffuse out of the tubular lumen. And two, the lowered intracellular concentration causes additional sodium ions to be reabsorbed through the luminal membrane. This provides more sodium ions to be actively transported and enables the cycle to repeat. In addition, as we will see in the following pages, sodium ion transport enables the reabsorption of most substances in the nephron.
I summarize this. These are basolateral membrane, these are luminal membrane. Interstitial osmolarity increases, causing water to diffuse. When increased osmolarity in interstitial fluids, it will help diffusion water, okay? And this lower intracellular concentration causes additional sodium ions to be reabsorbed through the luminal membrane. Next is a basolateral transport, active transport in this basolateral membrane.
We will now begin a tour through the renal tubules. We'll see how the specialized cells in each region accomplish a different stage of filtrate processing. Our first stop is the proximal convoluted tubule, where major reabsorption of valued substances occurs. We'll look first at the activities occurring at the basolateral membrane of the tubular cells. Click the box on the basolateral membrane to start the tour.
These are basolateral membrane, and see this
the reabsorption of many substances from the glomerular filtrate in the PCT depends directly or indirectly on the active reabsorption of the sodium ion. The cellular structure responsible for this process is the sodium-potassium ATPase ion pump located in the basolateral membrane. Orient yourself to the parts of the scene and then click the sodium-potassium pump to activate it.
These are sodium-potassium pumps, which are located in the basolateral membrane.
The ion pump carries out primary active transport of sodium ions out of the cell and potassium ions into the cell.
Exchange 3 sodium ions to the 2 potassium ions. These are basolateral membrane, which have this sodium-potassium pump first time from this luminal membrane, enters this sodium ions from to this it's named secondary active transport. With secondary active transport, glucose and sodium molecules enter inside the cells, and the sodium ions after from sodium potassium pump go in the interstitial space. Okay, 1 minute, I again enter.
Sorry, can you please repeat that? You know, this you said the secondary transport.
Okay.
You know, the primary, which is active transport, which is understandable. Then the secondary, because I was confused there.
Okay, 1 minute.
The interstitial osmolarity increases, causing water to diffuse out of the tube.
This first time you see, if you tell them about, ask me.
The luminal membrane of the proximal convoluted tubule contains many transport proteins. Here you see 3 sodium hydrogen countertransport carrier molecules and 2 sodium glucose cotransport carrier molecules.
These are sodium glucose cotransport. These
the
are
activity of all these
luminal
molecules depends on sodium potassium ATPase ion pump activity in the basolateral membrane.
It's a second
click
membrane.
any of the transporters to see their activity. When you have seen each, click the luminal membrane to see the activity of the entire membrane.
About this sodium
the
glucose
cotransport or symport carrier molecules carry both sodium and glucose into the cell. The reabsorption of glucose.
So when we have co-transport, it means it's secondary, yes?
High extracellular to low intracellular concentrations. This is an example of secondary active transport. Glucose now moves down its concentration gradient to the basolateral membrane, where it is transported into the interstitium by facilitated diffusion, as seen previously. Now click a sodium hydrogen transporter to see its activity, or click the luminal membrane.
Before I click this sodium second type of cotransport, I explain about this. 1 minute, I close this. You see this sodium glucose cotransport. Yes, these are simple. Both are moves in one direction, the same direction. What it means? These are secondary active transport. These are which type of membrane? These are luminal membrane, which are around this tubula, proximal convoluted tubes lumen. Yes, and the next way after first time sodium and glucose enter from this secondary active transport, and after enter in cytoplasm, and from cytoplasm then in basolateral membrane sodium ions are moved out from this sodium potassium pump active transport, and glucose are go into interstitial space from this facilitated diffusion. Now first time it's I repeat, these are which membranes? These are luminal membrane near this lumen of this proximal convoluted tube, which are has this one co-transport carrier molecule sodium glucose, and also second types okay, and basal.
We will now begin a tour through the renal tubules. We'll see how the specialized cells in each region accomplish a different stage of filtrate processing. Our first stop is the proximal convoluted.
No, first time luminal membrane, then cells.
The luminal membrane of the
first
proximal
this one and
tubule
this
contains many transport proteins. Here you see 3 sodium hydrogen countertransport carrier molecules and 2 sodium glucose cotransport carrier molecules. The activity of all these carrier molecules depends on sodium potassium ATPase ion pump activity in the basolateral membrane. Click any of the transporters to see their activity. When you have seen each, click the luminal membrane to see the activity of the entire membrane.
Okay, now this activity you see sodium, hydrogen,
the countertransport or antiport carrier molecule
these are antiport.
Carries a sodium ion into the cell and in exchange secretes a hydrogen ion into the filtrate. Here in the PCT, This activity is dependent on the movement of a sodium ion down its concentration gradient from high extracellular to low intracellular concentrations. This is an example of secondary active transport driven by the primary active transport of the basolateral membrane. The hydrogen ion being secreted here is generated in the cell for acid-base balancing purposes. Now, click a sodium glucose transporter to see its activity, or click the luminal membrane.
No, these are sodium hydrogen co-transport is an antiport, yes? But why? Sodium hydrogen ion out and sodium enter, yes? Which are also named secondary active transport. But primary active transport in the basolateral membrane, when sodium potassium pumps are activated and the pumps 3 sodium ions out and 2 potassium inside, okay? Is a second membrane, a two membrane, yes? First, luminal membrane, in opposite space are basolateral membrane. In basolateral membrane, sodium potassium pump, active primary transport. In this luminal membrane, two type of co-transport, symport and antiport. Symport with the sodium glucose
Transport or symport carrier molecules carry both sodium and glucose into the cell. The reabsorption of glucose depends on the movement of a sodium ion down its concentration gradient from high extracellular to low intracellular concentrations. This is an example of secondary active transport. Glucose now moves down its concentration gradient to the basolateral membrane, where it is transported into the interstitium by facilitated diffusion, as seen previously. Now click a sodium hydrogen transporter to see its activity, or click the luminal membrane.
Okay, these are luminal membrane. You see this two types of co-transport, symport and antiport. And also I again enter in basolateral membrane where sodium potassium pumps are located in this.
We will now begin a tour through the renal tubules. We'll see how the specialized cells in each region accomplish a different stage of filtrate processing. Our first stop is the proximal convoluted tubule, where major reabsorption of valued substances occurs. We'll look first at the activities occurring at the basolateral membrane of the tubular cells. Click the box on the basolateral membrane to start the tour.
These are luminal membrane, these are basolateral membrane. In luminal membrane, these are luminal membrane with your brush border also. And you
see the reabsorption of many substances from the glomerular filtrate in the PCT depends directly or indirectly on the active reabsorption of the sodium ion. The cellular structure responsible for this process is the sodium-potassium ATPase ion pump, located in the basolateral membrane. Orient yourself to the parts of the scene and then click the sodium-potassium pump to activate it.
Then sodium-potassium pump activated.
Using energy from ATP, the ion pump carries out primary active transport of sodium ions out of the cell and potassium ions into the cell.
Into the cells. 3 out, 2 in. 3 potassium.
As it yields its energy, ATP is converted to ADP and an inorganic phosphate ion, or PI. The sodium-potassium pump is found in the basolateral membrane of many regions of the nephron. Now click the ion pump again to see its effect.
No, again you didn't know, but in this basolateral membrane, I have this sodium-potassium pumps.
Watch what happens to the fluid in the interstitial space as a result of the ion pump's activity. Notice that the interstitial fluid is becoming more concentrated, as indicated by the darker color.
Dark color.
The net effect of the ion pump's activity is to decrease the sodium ion concentration inside the cell and increase its concentration outside the cell, thereby increasing the interstitial osmolarity. However, this increased osmolarity around the PCT soon draws water from the tubule, decreasing the interstitial osmolarity again, and together the water and solutes diffuse passively into the peritubular capillaries and are carried away. If you didn't notice the interstitium darkening, repeat the activity by clicking the ion pump.
Okay, you understand?
Otherwise, click the basolateral membrane to see additional features.
Yes, active is clear. Active transport is clear, yes.
Okay. You understand? Yes, these are primary active transport and secondary in this luminal space. When are co-transport, symport and antiport. Click this basolateral membrane.
Now notice two additional transmembrane proteins in the basolateral membrane, a potassium ion channel and a glucose carrier molecule. Click either protein to see its activity. The glucose carrier molecule binds only to glucose and transports it across the basolateral membrane by a passive mechanism called facilitated diffusion. Glucose can move either into or out of the cell depending on its concentration. Since in the situation shown here, its concentration is highest in the cell, glucose moves out of the cell into the interstitium. Now click the potassium ion channel to see its activity. The potassium ion channel lets most of the potassium ions diffuse from the tubular cells back into the interstitium. It prevents the sodium-potassium ATPase ion pump from causing potassium ion depletion in the blood or excess accumulation in the cells. In addition to the molecules you see here, many other substances also cross the basolateral membrane by similar mechanisms.
Which mechanism you see in this basolateral membrane? Active transport with sodium-potassium pumps, which needs this ATP energy. It's primary active transport, which sends these ions from low to high concentration. Also, this ATP are hydrolyzed from ADP, an inorganic phosphate, and release this energy. And from this energy, 3 molecules of sodium pumped from into the out, and 2 molecules potassium out to in. After you see this dark color means but more concentrated or osmolarity increase in this interstitial space. Next, these 2 molecules which are entered and prevents of accumulated of potassium ions are have, you see this potassium pumps which are you know are has this how many types of channels? Leakage channels which are always open when are passive transport from high concentration to low concentration, and also active transport. These are active channels which are voltage regulated channels which are open and closed by this change of this voltage. And active transport, one of the secondary, primary and secondary active transport. In this luminal space, luminal membrane, have this co-transport, secondary active transport mechanism, sodium, hydrogen, and the sodium glucose channels, symport and antiport, which are names secondary active transport. And in this basolateral membrane, you see this primary active transport with sodium potassium and also glucose molecules, glucose ion channels, when glucose from passive transport, facilitated diffusion, its name, inside this cell are more concentration of glucose and outside in the intercellular space less. These are facilitated diffusion, and these leakage channels are accumulation potassium ions inside the cells. Yes, inside, go from inside to outside. And these are basolateral membranes. Next, no luminal membranes activity. You see, effect of hyperglycemia. Hyperglycemia, you know, is a increase of glucose in blood. Hyperglycemia.
Glucose is vital to the body's normal functioning. However, in hyperglycemia, a condition that accompanies the disease diabetes mellitus, excess glucose accumulates in the blood. What do you think will happen if the number of co-transport molecules is not sufficient to handle an abnormally high concentration of glucose in the filtrate? Click the box next to the correct answer.
Please reading options and answered me. If what happens of this number of co-transport molecules is not sufficient to bundle abnormally high concentration of glucose in the filtrate. If in high concentration, infiltrate. And in blood is low concentration, which is correct answer. Please, first, co-transporter will have to work faster. Not all glucose will be reabsorbed. It will take longer for all glucose to be reabsorbed, or tubular cells will move co-transport carriers. Which one is correct?
Second option is correct.
Second option is correct. Very good.
Yes, the transport maximum has been exceeded. The extra glucose will be excreted in the urine.
And when this extra glucose excreted in the urine, its name, what is its name? Glucosuria. Glycosuria. Guys, these are glucose reabsorption, very good, interesting analogy. When high concentration.
The concept of transport maximum is much like this factory analogy. A fixed number of workers is matched to the maximum number of sacks of sugar they can remove from a moving conveyor belt. Under normal conditions, all sugar is removed because the number of workers and their rate of work is adequate to remove all of the sacks from the belt. However, if the number of sacks moving down the belt is increased, the workers cannot handle the extra load while working at their normal rate. They will remove only their normal amount, and the excess sugar will end up as waste. Now increase the blood glucose concentration by clicking the Increase Sugar Rate button.
Increase. Normal, you see this analogy. Increase.
What you are now seeing is analogous to the condition of hyperglycemia resulting from diabetes mellitus. Excess sugar in the filtrate exceeds the transporting capacity of the available carriers in the cells of the proximal convoluted tubule. Therefore, some of the sugar is not reabsorbed and so is excreted in the urine.
Okay, I think it's very good analogy. You see when this...
one question, please.
What question? No, you see this, but you see, but some of this... you have questions. Please, I listening.
Yeah, hyperglycemia. Hyperglycemia, not just in diabetes mellitus. Sometimes we can have acute hyperglycemic state after a carbohydrate consumption, for example, after we eat or something. So in this, it means that every time we will eat sugar, we will find the sugar in urine, which is not the case. So the body will compensate in hyperglycemic state in a normal situation, physiological situation.
Yes, no, it's normal rate. If you eating and your pancreas is release normal insulin, which regulates the sugar in blood, but it's not to have effects of hyperglycemia in short times. When you're eating this more no cakes example, yes, but if what means transport mechanism maximum reabsorption, if in this blood hyperglycemia in this long time, not in the short time. I will not release this example insulin, which are open the cells and enter glucose inside the cells, which are convert this glucose into glycogen. Yes, in the liver cells. But these are short time when your body is regulated. But diabetes mellitus, yes.
So if we find some glucose in urine after eating, for example, carbohydrate, it's normal.
Yes, it's after how many hours? After 2 hours, it's normal. After eating. Yes, first time decrease, but increase this excretion of insulin. Then this normal.
So it's insulin dependent. It's not for kidney work. Another question, please, doctor. Can I ask another question, please?
Yes.
Concerning the co-transporter, the secondary transport, primary glucose enters, sodium will enter. So a hyperglycemic state always will cause hypernatremia. Is it true as a condition, physiological condition?
Hypernatremia. When is hypernatremia? In outside, in this tubular, in this provisional urine test?
Hypernatremia, blood.
Hypernatremia in blood. Okay. If hypernatremia in blood, but co-transport also, which are one of these factor which are enter inside this glucose, also are increase this transport of glucose. Yes, from co-transport, from secondary active transport. If increase in this blood sodium ions, but also provisional urine.
As a result, I speak. For example, a patient with diabetes mellitus, we can find a lot of sugar in his before it.
You tell these two factors. Yes, one of these.
Yeah, they are dependent.
Okay, yes, yeah, but I tell about this next way. If hyperglycemia, if hypernatremia, yes, but in blood is increase of sodium ions, and then when makes this after filtration provisional urine, it's same concentration of sodium ions in blood and in this if isosmos, yes, if normal. But if high concentration of sodium ions, yes, but it reabsorb this more concentration, more this glucose molecules from this urine into this blood, and also are more increase this sugar level in blood. You tell this one or no?
I understand. Thank you, doctor.
Okay. No, one of these factors is hyperglycemia when this not release this normal concentration of insulin, and second, also one of the factor is increased sodium ions in blood, natriemia, yes, in this blood. And when this normal sugar levels is 5.5 to 6.6 millimole per liters, yes, and if we increase this in blood, this concentration of sugar, example 10 millimole per liters, then all glucose is not reabsorption, and some extra glucose are go in this urine, all not reabsorption when high concentration in blood. Yes, but why? Second, from but from basolateral membrane are enter from facilitated diffusion, and from high to low concentration, it's a passive transport. Also from passive transport enter glucose into the endothelial cells of this peritubular capillaries, and if this a high concentration, it's all glucose not reabsorbed, or some are go in urine, and it's named glycosuria. Yes, I transport maximum. It's named glycosuria. Then next is a paracellular pathway.
The second reabsorption route, the paracellular pathway, uses the small space between cells as a passageway.
From tight junctions, also these are paracellular pathway, intracellular pathway. Okay, now first time continue your presentation. I tell about this way. It must first transport across the tubular epithelial, then renal interstitial, and this one. Okay, next this slides. 1 minute. What you see, these are peritubular capillaries. These are luminal membrane or luminal space, and this one is a basolateral membrane and the interstitial fluid. These are basement membrane, and these are in the interstitial space, and these are peritubular capillary, as is always. A luminal membrane, then these cells, epithelial cells, which are if this proximal convoluted tube, which are names, this simple cuboidal epithelial cells. Next, this is basement membrane and basolateral membrane. After enter with this membrane, and you see this interstitial fluid, and after enter in this peritubular capillary. Sodium potassium pumps. Where is this one? Transport sodium from this inferior of the cell across this basolateral membrane, right? This basolateral membrane, and creating a low intracellular sodium concentration and negative intracellular electrical potentials. Then allow intracellular sodium concentration and the negative electrical potential cause sodium ions to diffuse from the tubular lumen into the cell throughout the brush border, through the brush border. Now, you see this Cl ions transport in this for reabsorption passive transport, sodium transport active transport, and water follow salt by osmosis. Next, and this one also interesting, mechanics of reabsorption in the proximal tubules. These are the same slides, but you see this. What is this? These are cells of proximal tubular cells, interstitial fluid between, and these are blood vessels. Types of transport, co-transport in this space, yes, two types. First, molecules that are reabsorbed pass through the tubular cells from the apical membrane or facing infiltrate to the basolateral membrane facing the blood. This is a coupled transport or secondary active transport of glucose and the sodium ions enter into the cytoplasm, and primary active, these are primary active transport when ATP are converted with ADP and inorganic phosphate. These are primary active transport, and these are secondary active transport, co-transport with this sodium glucose co-transport with sodium glucose and symport and antiports, hydrogen ions and the sodium ions. And this next, in this basolateral membrane, you see this facilitated diffusion. From facilitated diffusion are go examples is glucose and other substances, and then from simple diffusion are all this one, and these ions also are enter inside these blood vessels in blood. Primary active transport of sodium across this basolateral membrane by the sodium potassium pump, and glucose is then transferred out of the cell by facilitated diffusion and reabsorption into the blood. First, this transport names co-transport in this luminal space of this membrane. In the basolateral membrane are two types of transport. First, facilitated diffusion, example, a glucose transport, and second is a primary active transport. Understand this transport in these two membrane, luminal membrane and this basolateral membrane. Understand? Yes or no?
Yes, yes.
Okay. Next, 65% of the salt and water in the original glomerular ultrafiltrate is reabsorbed across this proximal tubule and returned to the vascular systems. The volume of this fluid is still isosmotic with the blood, which has a concentration of 300 milliosmol. This is because the plasma membranes in the proximal tubule is freely permeable to water, so that water and salt are removed in the proportional amount. Next, in additional small amount of salt and water, about 20%, is returned to the vascular system by reabsorption through the descending limb of the loop of Henle. And reabsorption, like in the proximal tubule, occurs are constantly regarding of the person's state of hydration. Approximately 85% of the filtrate, salt and water, in reabsorbed in the constant fashion in the early regions of the nephron, proximal tubules, and loop of Henle. I think which time? Okay, if you want 10 minutes break time, yes, and after continue. If you did not want break time, I continue
Yeah.
with
Yes.
10,
Thank you. 10-minute break. Thank you
10
very much.
minutes.
Yeah.
Okay,
Thank you.
okay, 10 minutes break. Yes. Very good. About paracellular pathway, continue. These are the absorption I tell. And 85% of original glomerular ultrafiltrate is reabsorbed in the early regions of the nephron. Only 15% of the initial filtrate enters the distal convoluted tubules and collecting duct. And how much this 15% of 180 liter per day is a 27 liter per day. This is still a large volume of fluid that must be reabsorbed by varying degree in accordance with the body state of hydration. This counter current multiply systems from ascending limb of the loop of Henle and descending loop of Henle, also around of this descending and ascending axis vasa recta, yes, these blood vessels which are help also reabsorption water and salt. Water cannot be actively transported across the tubular wall. First time see this different summary reabsorption in PCT and then reabsorption in thin descending loop of Henle.
To summarize the activities of the proximal convoluted tubule, sodium-potassium ATPase ion pumps in the basolateral membrane drive the reabsorption of water and solutes by increasing the sodium ion concentration of the interstitium. Hydrogen ions are secreted into the filtrate to provide an acid-base balance. Abundant channels and transport molecules in the luminal membrane provide passage for solutes to move down their concentration gradients between the filtrate and the cytosol of the cell. Water and solutes move by bulk flow from the interstitium into paratubular capillaries to complete their reabsorption process. As a result, valued substances have been reclaimed. Approximately 65% of the filtrate is reabsorbed into the paratubular capillaries from the PCT. Included in this reabsorbed volume is virtually 100% of the filtered glucose, amino acids, and any proteins that may have escaped from the glomerulus.
This is a summary about proximal convoluted tube. These are glucose which are entered from this lumen of this proximal convoluted tube. This way, first is luminal membrane, then basolateral membrane, and then three types of transport. Yes, first is a co-transport with sodium ions, then is facilitated diffusion in basolateral membrane, and after simple diffusion, which are entered in this blood glucose. And T maximum is a maximum concentration of glucose which are in this blood. These are two units. First, from 80 to 120, maximum 125 gram per liters, and also has this millimole per liters. 5.5 to 6.6 millimole per liter. These two units. And if increase this sugar levels, and it's increased when this disease diabetes mellitus, when this insulin from these beta cells of islets of Langerhans of pancreas not produce this insulin, then glucose levels is increasing in blood. It's named hyperglycemia, and these extra glucose are also present in urine, and its names glycosuria. Glycosuria, when glucose present in this urine, is a pathology. In these three ways, co-transport with sodium ions, simple, then facilitated diffusion, also this passive transport, and then enter from simple diffusion in the blood vessels. Also, some water, these sodium ions transport is active transport in basal lateral membrane with active transport concentration of urine in this interstitial space is increased, and its name also hypernatremia. Hypernatremia is terms when increases sodium ions in blood and also in interstitial space. This concentration of increase of sodium ions in this interstitial fluid leads to increases osmolarity, which are need reabsorption water, different concentration of water. Next is a reabsorption of thin descending loop of Henle. A thin descending loop of Henle is a different types of cells.
As the tubule transitions from the proximal convoluted tubule to the thin descending loop of Henle, it straightens and dips into the medulla, and its epithelium changes from cuboidal to flattened squamous cells. As in the PCT, the cells here are permeable to water, allowing diffusion in response to osmotic gradients. The increasingly high osmolarity of the medullary interstitium provides a strong osmotic gradient that pulls water out of the filtrate. Recall that sodium and chloride ions and most solutes cease to be reabsorbed in this region because the flattened cells lack transport proteins. As a result of these conditions, a great deal of water leaves the filtrate, while solutes are retained. This causes the filtrate to become increasingly concentrated as it passes down the tube. Notice the higher osmolarity of the filtrate at the lower end of the tubule, as shown by the darker color.
Next, you see this loop of Henle, which have this descending part, thin descending, then thin ascending, and thick ascending part. They change these epithelial cells from simple squamous epithelial cells, which are present in this proximal convoluted tube, are has this simple cuboidal change with the simple squamous epithelial. Epithelium are transition from cuboidal epithelial cells, the simple squamous epithelial cells. And membranes are permeable to water, but not sodium cells. Why? Is water are permeable when are osmolarity is concentration in this interstitial fluid are salts, which are regulate this ascending limb of loop of Henle. Why? It increase from sodium ions, and the sodium ions are increase this osmolarity in this around this ascending limb, which are helping different concentration of osmolarity interstitial fluid around this descending and ascending limb are formations, this concentration gradients, and this water are permeable from this descending loop of Henle. But is a one layer, simple squamous epithelial cells, very thin layer, and water reabsorbed simple.
Toward the cortex, the thin squamous cells transition to simple cuboidal cells of the thick ascending limb. Water permeability of these cells is greatly restricted by tight junctions and by a glycoprotein layer that covers the luminal membrane.
Two factors.
Click the box on the luminal membrane to see the activity there.
Why not permeable water in ascending loop of Henle? Why? First time, these tight junctions, and second is a glycoprotein layer inside this luminal membrane, and it's permeable from sodium ion salts, but not permeable to water. This water permeable restrict by tight junctions, and the glycoproteins covered of the luminal membrane. You click this.
Looking at the luminal membrane of these cells, we see that they lack a brush border in contrast to the cells of the proximal convoluted tubule. However, they do have a limited number of short microvilli containing many ion channels and secondary active transport molecules. Now click the co-transport molecule to see how it differs from the one shown for the PCT.
These are different co-transport with this PCT. Which is different?
Notice that the secondary active transport molecule is not the same carrier as the sodium glucose co-transporter in the PCT. Instead, this carrier molecule co-transports a potassium ion and two chloride ions. However, just as with the sodium glucose co-transporter, it is the sodium ion moving down its concentration gradient that drives this activity. The import of potassium does not increase the cell's potassium concentration.
But why?
Because these ions diffuse back into the filtrate through the potassium ion channels in the luminal and basolateral membranes. The imported chloride ions follow the sodium ions through the cytosol to the basolateral membrane.
Now you see this basolateral membrane of this ascending loop of Henle, which are not luminal membrane, sorry, which are different with this proximal convoluted tubes. In proximal convoluted tubes, you remember has this co-transporter systems from sodium hydrogen ions and sodium glucose ions, contrastimpers and antipers, which are using the secondary active transport. And you see this in luminal membrane also has this co-transport systems, but different. Why? You open and send how much? Two Cl ions, one potassium ions, which are not accumulate inside the cells, but you see these two potassium channels and also sodium ions. It's a difference between, also our brush border are less than in this proximal convoluted tube, and different types also co-transport systems in this luminal membrane of ascending loop of Henle. After the ascending loop of Henle, which are have the simple squamous epithelial cells, it also change with these cuboidal cells. But cuboidal cells lack brush border, and also co-transport systems in luminal surface are different. It's pumped two Cl ions, also potassium ions and sodium ions. Potassium moves from inside to outside, not concentrate inside, and the Cl ions from this basolateral membrane. After I see basolateral membrane, reabsorption of ascending loop of Henle. These are luminal membrane with your co-transporter systems.
Now let's look at the activities of the basolateral membrane of these cells. These cells possess the same sodium-potassium ATPase ion pumps and potassium channels as do the cells of the proximal convoluted tubule. As seen previously, these pumps generate a sodium ion concentration gradient that drives the reabsorption of other substances through the luminal membrane. Notice also the chloride channel, which allows chloride ions entering from the luminal membrane to follow sodium ions out of the cell. Click a sodium-potassium pump and watch the interstitial osmolarity change.
These are basolateral membrane, sodium potassium pumps.
The increasing osmolarity of the interstitial fluid is the result of sodium, chloride, and potassium ions being reabsorbed from the filtrate and transported into the interstitial space. The restricted diffusion of water out of the filtrate, as seen on the previous page and in this pop-out view of the tight junction, prevents equilibration of the filtrate and interstitial fluid. The cells of the ascending limb of the loop of Henle are able to maintain an osmotic difference between these two fluids of approximately 200 milliosmoles.
Difference between each
The significance of this reabsorption pattern will be explained later in this topic.
Now, first time what you see this basolateral membrane with your sodium potassium pumps, active transport also, but sodium are increased osmolarity in the interstitial fluid, and different osmolarity in this medullary region, a deeper region, and in the cortical region also different. Normal in proximal convoluted tube, are 300 milliosmoles, and in deeper region of this medulla are sometimes 4 times are more 1,200 milliosmol, and up is a small decrease this osmolarity. I see osmotic gradients between this interstitial fluid and tubular filtrate is approximately 200 millimoles difference between extracellular fluid and intracellular. Why not permeable water? Is this ascending loop of Henle? Why? Inside you see this glycoprotein membrane, yes, and also tight junctions, which are not permeable this water, and which are result if water are permeable in this ascending loop of Henle, it's not concentrate this osmolarity, not increase in this interstitial space. No summary of ascending and descending loop of Henle difference, osmolarity.
In summary, as a result of solutes being removed from the filtrate and water being retained, there are two very important effects. One, the filtrate becomes increasingly dilute as it moves up the tubule. And two, the osmolarity of the interstitium is 200 milliosmoles greater than the osmolarity of the filtrate at any given level of the tubule. Notice particularly that this has also formed an osmolarity gradient from the bottom of the interstitium to the top. In this medullary osmotic gradient, the osmolarity of the deeper region is greater than that of the region close to the cortex. Now click and drag a milliosmoles box to compare the osmolarities of the filtrate and interstitial fluid. Then click the next button to see how the activities of both the descending and ascending loop of Henle combine to construct and maintain this medullary osmolarity.
Sorry, doctor, you exit the video, so please you exit the video.
Exit. Why?
Yeah, I mean you are now we can't see the slide now.
Ah, you see the slide now?
No, we can't see this.
No, why?
You accidentally clicked stop sharing, that's why.
Ah, I click stop share. Okay, sorry. At this moment, you see this video?
Yes, now we can see again.
Yes.
Oh, okay. So these previous slides also you did not see?
Oh no, it was just this slide.
Only this. Okay. Now you see difference between 600 and 800. Difference is 200. This interstitial osmolarity is 200 millimoles greater than filtrate and given. And in different states, I see it's change in deeper region of this medullary are more, but all times concentration gradient is 200. I differ 751 minus 55, 551. I this one, you see, in upper region are concentration gradients is same, but decreases osmolarity in this cortical rate. Next is countercurrent multiplication.
To demonstrate the current theory of how the loop of Henle forms the medullary osmotic gradient, here's a simplified view of the cortex and medulla. This theory is called the countercurrent theory because of the opposing flow of filtrate within the two limbs of the loop. The complex interplay of the ascending and descending limbs forms and maintains an interstitial osmolarity with a gradient from approximately 1200 milliosmoles near the bottom of the loop to the normal 300 milliosmoles near the cortex.
300 milliosmoles you see in this cortex. In medulla deeper region, 1,200 is 4 times more. Also, you see these colors, deep colors, means more osmolarity, and this up is less osmolarity. Inside also these tubules, when after proximal convoluted tube are distal, are this descending loop of Henle. Then ascending loop of Henle, and these are distal convoluted tubes.
The gradient formed by this activity is essential for the concentration of urine. To demonstrate how the gradient is formed, we will look first at the role of the ascending limb of the loop and then at that of the descending limb, because the ascending limb creates the conditions necessary for the descending limb to function. Click the ascending limb to begin.
First time ascending limb.
The ascending limb of the loop actively transports sodium chloride into the interstitium, increasing its concentration while restricting the diffusion of water. The interstitium surrounding the tubule becomes more concentrated, while the fluid inside becomes more dilute. As the fluid moves up the loop, there is progressively less solute to pump out, so the highest concentrations of solutes are near the bottom of the loop.
These are
now click the descending limb to continue the process.
First time this is descending, and then I
the role of
summarize.
The descending limb in this process is to provide a continuous concentrated supply of sodium chloride to the ascending limb. The filtrate concentrates as it moves down the descending limb because water diffuses into the higher osmolarity interstitium created by the ascending limb. The solutes remaining in the tube reach a concentration approximately 4 times higher than normal body fluid. The effect is much like what happens in the Great Salt Lake when water evaporates and salt is left behind. The fluid that is left is very salty. This salty filtrate provides a ready supply of sodium chloride for the ascending limb to maintain the osmotic gradient.
No, in this ascending.
Now click the interstitium and watch the combined but asymmetric activities of the two limbs as they build the osmotic gradient. The way the two limbs cooperate to multiply the solute concentration from the normal 300 milliosmoles of the cortex to a level 4 times higher in the medulla is called the countercurrent multiplier mechanism. This mechanism has also diluted the luminal fluid in the ascending limb to an osmolarity of approximately 100 milliosmoles. As a result, water is retained while solutes are removed. This graphic now shows the 200 milliosmole difference between filtrate and interstitium developed by the cells of the thick ascending limb.
No, you see this normal osmolarity difference between in the cortex and medulla.
Yeah, can I ask you one question? Because is that okay for me? Yeah, in descending, you find out that the sodium is restricted in descending.
Yes.
And in ascending, the water is restricted.
Yes.
So if you have that water and sodium restricted, and where is the most concentrated, highly concentrated, going to be stored in that stage?
No, I did not know the second part of your questions, but I answered what you understand. 1 minute in this descending loop, descending loop of Henle only permeable from this water. Why? It's help your friend or second part ascending limb of loop of Henle, which are permeable from this sodium ions.
No, my question is that my question is that where is the most solute going to stay in the loop? Where is the most high concentration of the solute going to stay if you have the water being restricted in the ascending loop and you have sodium being restricted in the descending loop? Where will be the highest concentration of the solute, please?
Ions concentration, this sodium ions, and this in proximal convoluted tube. You see this moves the sodium ions in this proximal convoluted tubes, this luminal space and this basolateral space, and after enter in the blood. This moves in the proximal convoluted tube, reabsorption in this proximal. But in this descending loop and ascending, it are regulate water concentration volume of water inside this lumen and in this blood also. But why this ascending? It's permeability only from this water, and when permeable water outside is osmolarity is decreased. But in ascending limb loop of Henle are permeable from sodium ions sodium ions, but not water. Why not water? Tie junctions and also glycoprotein inside, yes. And this when water is not permeable and permeable only sodium ion, it concentrate this interstitial fluid. And difference between osmolarity in the interstitial fluid and inside are permeable water in descending loop of Henle. It's help our permeability of water in descending loop of Henle. And sodium ions are permeable in this ascending limb from inside to this interstitial fluid. It's concentrate osmolarity in this interstitial fluid. And difference you see in this deeper region are 100, 1200, and in this cortical 300 also are different inside this urine are sometimes dilution and sometimes are concentrate. If more water you see how much I 1000 in this deep of medulla, and then sodium ions move out, and out is sometimes are more osmolarity have, inside are less. Permeability of sodium ions in this distal, no, but in sodium ions and Cl ions also are permeability in this ascending limb, and sodium plus Cl are make sodium Cl salt, which are increase osmolarity in this interstitial fluid. You not understand?
Yeah, thank you. Thank you very much. Thank you.
Okay. Okay. Next is a vasa recta also, our counter current exchange, but after this descending and ascending, which are have this opposite direction urine, yes,
We must
from
now
the
address the
and
problem of
then
how to keep the solutes in the medullary interstitium from being carried away
around.
by the blood. The cells of the medulla require nutrients to function properly. However, blood in a normal capillary flowing through the medulla would also reabsorb and remove massive amounts of solutes from the medullary interstitium. This would quickly weaken the osmotic gradient. To avoid this problem, the capillaries of the vasa recta, as shown here, form hairpin loops, enabling them to function as countercurrent exchangers. Click the vasa recta to see its function.
After this ascending or
Here we see a
descending loop
simplified view
around
of one loop of the vasa recta.
one loop.
Blood in the vasa recta loops delivers nutrients such as glucose and oxygen to the cells of the region. At the same time, the loops function as countercurrent exchangers of sodium chloride and water. The exchange mechanism works as follows. Blood moving down the descending portion of the vasa recta loop passes through areas of increasing osmolarity. Responding to osmotic pressure, water diffuses out of the blood into the interstitium. At the same time, sodium chloride diffuses into the blood as a result of its higher concentration in the interstitium. If this blood now left the medulla, the sodium chloride would be removed and lost to the osmotic gradient. However, the capillary actually reverses direction, so the conditions also reverse. The viscous blood moves up the ascending portion of the vasa recta through areas of decreasing osmolarity. The blood regains the water by osmosis and loses most of the solutes back into the interstitium.
Which are
The
removed.
net result is that the blood has brought nutrients to the cells of the medulla without carrying away extensive amounts of solute, which would weaken the osmotic gradient.
And this all information you have in your presentations, this hypertonic solution, isotonic solution, where is and the ascending limb is divided into 10 and 6 segments, you know. In salt is actively extruded from the 6th segment of the ascending limb into the surrounding interstitial fluid. In the cells of the thick portion of the ascending limb, the movement of sodium ions down is electrochemical gradient from the filtrate into the cells. Powers the inward secondary active transport potassium and Cl ions. This occurs as ratio of one sodium 1 potassium and 2 Cl ions. You see in this luminal membrane different types of co-transports. Instead of proximal convoluted tube, we have two types: sodium glucose and sodium hydrogen co-transport. And in this secondary active transports are open and moves how many? This 2 Cl, 1 potassium, and 1 sodium ions. You see in animations this also. Next, about this counter current multiply systems, the extrusion of sodium chloride from the ascending limb makes the surrounding interstitial fluid more concentrated. When sodium ions and Cl ions also are moved, sodium plus Cl is a salt, sodium Cl. And these are surrounded, makes this interstitial fluid more concentrated. And multiplication of this concentration is due to the effect that the descending limb is passively permeable to water, which causes its fluid to increase its concentration as the surrounding interstitial fluid becomes more concentrated. And the deepest region of the medulla reach concentration 1,400 milliosmoles. You see inside 1,400 milliosmoles. Next, these are transport ions in the ascending limb. Ascending limb, I tell, but is the sixth segment of the ascending limb of the loop. Sodium and potassium together with 2 Cl enters the tubular cells. After sodium is then actively transported out into the interstitial space, and Cl follows passively. Sodium ions, same with this proximal convoluted tube. It's reabsorption in different types of transport. First, from co-transport. Second, active transport. Same in this ascending limb also. But more concentration of sodium are reabsorption in this proximal convoluted tube. Only small portion are reabsorption from in this ascending limb. Yes, and it's from which type of transport? First time, this co-transport mechanism, which are different with this proximal convoluted tube. But why 2 Cl ions, 1 potassium and 1 sodium ions enter, move inside the cytoplasm. And then from this basolateral membrane, from active transport, same this proximal convoluted tube, in same transport ascending limb of loop of Henle, sodium, 3 sodium are changed with these 2 potassium ions, and also Cl ions, which are go from inside to the interstitial space with this passive transport. Passive, these are passive Cl, these are from active transport, which are use this ATP energy. And this salt is extruded into the surrounded fluid, and epithelial walls of the proximal tubules, however, the walls of the ascending lip of the loop of Henle are not permeable to water, no water. The filtrate is the ascending limb. This becomes increasingly dilute as they ascend into the cortex. By contrast, the interstitial fluid surrounding the loop of Henle in the medulla becomes increasingly more concentrated. In next slide, you also see this descending limb of loop of Henle, different osmolarity, I tell, permeable to water, descending permeable to water, ascending permeable to this salt, which is sodium ions and Cl ions. Sodium ions from in this basolateral proactive, these are from the passive transport. And because the surrounding interstitial fluid is hypertonic, hypertonic means more osmolarity. Yes, hypertonic. Why? It makes to the filtrate in the descending limb, water is drawn out of the descending limb by osmosis and enters blood capillaries. Next also our counter current multiply system. I think this next I continue in next lecture next week. Okay, please you prepare this presentation. And I explain also next lecture also about urinary systems, I think. And if you have questions, next week on Wednesday you have this seminar, and I answered about all your questions. Okay. Thank you listening and watching me today. But how many students? 14 students only. Instead of how much? Total, I think 200 students. Welcome, my dear students. Okay. Very bad. I did not see your face. Who are you? But no problem. I have Facebook. If you want my name, Lali Modebadze. And please send me, and I received my friends. If you want, Lali Modebadze found me on my Facebook, okay? And write questions also. Okay, bye-bye. Nach вам this. Спасибо, пожалуйста.
Doctor, when you will upload the slides on the drive?
Which slides? Presentation, PPT is not upload.
Not yet.
No, your deans or Lana tell me, but you yesterday upload this my presentation. Some students answered me, but you have this presentation. Not this, if you tell about this interactive physiology, it's not uploaded. It's very difficult to upload. Yes. About you tell me about IP10, interactive physiology.
Yes.
No, this is not uploaded one. No, you found in YouTube. If you write in YouTube, interactive physiology and urinary systems, you found the systems explanation. You found did not have quiz. No quiz. I open in next Wednesday when you have seminar. Okay. Okay. Goodbye, my dear students. Nach вам this.